Hello all. So today we will solve a finite element analysis of lead-free ceramic base, a Cymbal transducer for the energy harvesting. So here we can see this is the paper which are regarding the finite element analysis of the lead ceramic, and in that paper we can see this symbol structure where we can see the load is applied from the top side. So here we can see this is the geometry where this central layer will be piezoelectric crystal and this will be the metal. Okay, in between that there is what foam is added as insulator or substrate. Okay, so we will start to simulate this, and for that purpose we need to use the comsol Multiphysics software, and in that comsol Multiphysics software we will select the axis symmetric model. So for that purpose we have to open this comsol Multiphysics software, and then we have to click on the model wizard. Here we'll see this is the what 2D axis symmetric. After clicking on this we'll get this movie. Okay, so here we can see this is the structural mechanics, and in that structural mechanics we have to click on piezoelectricity. So we have to click on the piezoelectricity. So for that purpose we have to see this module, piezoelectricity of solid. So here we can see this module consists of the solid mechanics and electrostatic which are working together, and here when we apply electric crystal it will generate voltage. Okay, so it will take some time, and here we have to click on the study and we can see this is what stationary. Okay, so we are studying this module for the stationary load of the 100 Newton or 500 Newton. As per our requirement we can change this load. As per application also we can change the load. Okay, so this stationary load is what? That load is a constant in which will not change over a period of time. Okay, so here we can see first we'll draw the geometry for that. So we have to click on this geometry, and then we can see the unit which we have changed. So this is the axis symmetric, this is the axis, and then we have to select the rectangle, because here we can see this foam material is the first component which we add in this. Okay, so this is the h4 and that dimension of the h4 is the 0.30. okay, so here we'll select that and we'll give the width of that component is the 2 that is the 8 mm, and the height will be the 0.3. okay, so which will first. So here we can see this is the build component, but the axis is here, so we'll shift that component by a dimension. So here we can see after calculating these dimensions, here we can see this radius will be shifted by the 10 mm from the axis. So here this radius will shift by 10, then we'll build. So here we can see this is the shifted by the 10 mm. Next to that we will take duplicate of this rectangle. Okay, so here we will give dimension to this next rectangle. Okay, so here we can see this second rectangle we will try to draw here, and this width of this rectangle is how much? 18. After calculation we have, so here the height will be the 0.5. okay, and radius will be the 0 because it is starting from the axis, and the height of this rectangle is how much? That is the 0.3. okay, which we have completed. Next to that we have to draw we have to sketch with the help of the polygon from here to here. Okay, so this polygon we have completed, and we will see the dimension, how much dimension is here. Okay, so h2 will be the height, and that is the how much 0.5 from the this 0. Okay, so which we'll see here. So here the we'll get the polygon dimension. It is starting from 18, so height will be the 0.8. This starting point is here, second point is here, third is what, third point is here, and after calculation we'll get that point is 1.3, and then we'll build select. Okay, so here next to that we'll see this next point having the what, 1.3. Okay, so we have taken that dimension 1.3. Next dimension will be the what, how much, height of the 1.8. Okay, next to that here we can see his height will be the height of this point will be the how much, that is the 8, and next will be the 1.8. Okay, next point we'll see this point should be the at height of 1.3 as per the geometry. Okay, next this point will be the 1.3. Okay, so we have completed that. Okay, so this is the what, 0.8, and the dimension, that point should be the at 8. Okay, so we have successfully completed this geometry which we want to as per these paper dimensions, research paper dimensions. Okay, next to that here we'll take us transform, and we'll take care of this metal structure. Okay, so here this metal structure I want to shift at the bottom. Okay, so we'll get a geometry like this, axis symmetric geometry like this. So here I have selected these two components. Okay, I want to keep this object as it is. Okay, so for that purpose I have to take radius should be the 0, because I want to shift along this axis in the radius will be the 0, and I want to transform along the what, y-axis. So after building structure we will get this piezoelectric crystal structure. Okay, next to that we'll add the material for that. So we'll add the material of the aluminum from the material library. From this material library I want to select the aluminum material. So this is all material which are regarding what, aluminum alloy, but I want to what, I want to the pure aluminum, that is the solid. So from built-in tab I will select the what, aluminum, and which I will add to. So here material will be made up of from the aluminum. So I will add this. Okay. So I have selected one and second component. Okay. Next to that, here we will add the next material from this piezoelectric crystal. That is the piezoelectric material PZT5H. So from this we can see here, this is what lead zirconate titanate material, which I will add here for the piezoelectric layer, and these two materials are what made up of from piezoelectric. Okay, so which here we can see we have successfully added the material for the all these components. Next I will made this material as a foam. For that purpose I have to select this central component. Okay, next to that we will move forward, and here we will give the all boundary condition of the solid mechanics. So we have selected the all materials for this piezoelectric crystal, and here I will select the piezoelectric material from this solid mechanics, and where we can see these two components are only made up of from the what that piezoelectric central is made up of from foam material. Foam material I am adding as a substrate. Okay, next to that I will give the boundary conditions. So here at the bottom I will add the what X constraint. Okay, next to that I will add the load with the help of boundary load tab. This tab is here and I have given the load. Okay, so load is what total force which is in Z direction. So here I will give 100 Newton load in downward direction. Okay, next to that here in electrostatic, where we can see we'll give the boundary condition like ground. So here we can give these boundaries as a ground, and central will be act as what that will be the potential. So where we will get potential. Okay, so we have successfully added all these components. Now we'll check so which property we need to give. So central part is what or foam material, so where we will give all properties. Young's modulus of this will be the what Young's modulus we will give 35.3. Poisson's ratio or this will be the 0.383 for the foam material. Density will be the what 32 kg per meter cube. Okay, so all properties we have given. Next to that we will check for the aluminum. So we have successfully given all property to all components. So here for electrostatic we have to select only the two components, that is our piezoelectric. So I have selected the piezoelectric material for this electrostatic physics. Okay, so here I have added the multiphysics module where we can see the piezoelectric. It will interact with the what solid mechanics with the electrostatic, because when we apply Also on this piezoelectric crystal will be generate what? Voltage. So we'll do meshing. Here normal mesh also we can give, but I want to the more accurate results. That's why I have to select the extra fine and will compute all these results. It will take some time to solve. So here we can see here one mesh traces are getting developed. That is what 5 into 10 raised to 8. That much one mesh traces are getting developed into this structure, piezoelectric crystal structure. So here we can see in stresses in 3D also. Okay, so this in this area we can see the more stresses are getting developed. Okay. Next to that we can see the electric potential, where the 22 volt, that much voltage is getting developed in that piezoelectric crystal. Okay, so we can see the revolve geometry also. So here we can see how much maximum voltage is getting developed on top layer. Okay, here we can see the electric in normal direction also. Okay, so that is what 1.36 into 10 raised to 6 volt per meter, that much voltage is getting developed. Okay, so we have successfully solved this problem. Thank you.